All right, well, following sort of the same vein as last time where we did a product of vectors called the dot product. Now we want to make our main topic a product of vectors called the cross product. So this one exists only in 3 dimensions, although there's in physics, there's a 7-dimensional form of it that very few people care about. So for us, in 3 dimensions only, the cross product of 2 vectors is a vector. Unlike the dot product of vectors, we recall was a number. Dot product or the cross product is actually a vector. So if I take a vector with components v1, v2, and v3, a cross product with a vector with components w1, w2, w3, the result is a vector with these components, v2, w3 minus v3, w2. v3, w1 minus v1, w3. v1, w2 minus v2. And these subscripted things are, of course, the components. These vectors. So that can be the definition, if you like. Some people find that hard to remember. There's 2 important ways that people remember these. The first one is faster if you can remember, but if you don't use this all the time, maybe it's not worth trying to remember. I call it the 1, 2, 3 method. Anybody can count to 3. So what you do is you take the numbers 1, 2, 3, and if you've heard of permutations before, permutation is just an ordering, mathematical term for ordering. So if I take the digits 1, 2, 3, I can get different permutations, different orderings of them. And a cyclic permutation means that I just rotate the letters around into a different order. So if I rotate 1 around to the end, then I'll get rotate the 1 around to the end, then I get 2, 3, 1. Then I rotate the 2 around to the end, so I get 3, 1, 2. So these are cyclic permutations when you just rotate them around to the end. And those tell you exactly how to write this down. The first component of the product, right? This is the first component before the first comma, is 2, 3 minus the reverse order 3, 2. The second component is 3, 1 minus 1, 3. And the third component is 1, 2 minus 2, 1. So the cyclic permutations of 1, 2, 3 tell you what goes in here. The first thing is the component number, the last 2 are the order of the first V and W components. So that makes it pretty easy, I think. I remember it that way to be able to do these quickly. For example, suppose I took the cross product of 1, 2 minus 1 with 4, 0, 1. What do I get? Well, I take, for the first component, I take 2, 3 minus 3, 2, right? So I take 2 times 1 minus 1 times 0. 2, 3 minus 3, 2. For the second component, I take 3, 1 minus 1, 3. So minus 1 times 4 minus 1 times 1. And for the third component, I take 1, 2. 1, 0 minus 2, 4. That's it. It's pretty easy. But if you don't use it once in a while, it can kind of go away. Let's see. 2 minus 0 is 2. Minus 4 minus another 1 is minus 5. And 0 minus 8 is minus 8. The cross product of these 2 vectors is this vector. Maybe I should emphasize that is the vector. Given by this expression. Okay, so that can be equation 1, the definition of the cross product. This is not to be confused with the Cartesian product. Anybody seen the Cartesian product before? It's used quite extensively in mathematics, particularly in set theory. The Cartesian product, after the famous philosopher Descartes, who was also quite a good mathematician and got a lot of analytic geometry started. Cartesian coordinates are named after him. He's the guy who said, "I think, therefore I am." So he's a more famous philosopher, I think, French guy. Well, I'll lose my point here, so going off on here, but
Vectors.
no, from the Cartesian product I was going, sorry. The Cartesian product is like this. I put this on the side. This doesn't have to do with tonight's lecture. If I take the set AB, take the Cartesian product with the numbers 1, 2, 3, the Cartesian product of sets, it applies to two sets, not to two vectors, is the set of ordered pairs where the first element comes from this set and the second from this set. So it's the set of ordered pairs A1, A2, A3, B1, B2, B3. So I introduced this for your education to say, if you've seen this before, this is not what we're doing, don't get it confused. If you haven't, then this is a useful thing because we're actually going to use it later in the play. Cartesian products of sets when we get into more dimensions. Maybe not this semester, I'm trying to think, it might be next semester, but Cartesian product of sets will come up occasionally. So not this one. Cross product has that definition, number 1. All right, if this isn't easy enough to remember, there's another way to remember it that actually has more to memorize, but in the long run, you have to memorize this stuff anyway for mathematics in general. And since you have to memorize it anyway, it will make this actually easier to remember in the long run. So another equivalent definition is in terms of determinants of matrices. Here I said it's more to memorize now. What's a matrix? What's a determinant? All right. Fact is, in mathematics, I think calculus is sort of absolutely fundamental to a math degree and to a lot of sciences too. But the other thing that's really fundamental as far as pure mathematics goes is linear algebra. And linear algebra, matrices and determinants are foundational for that subject. So it's what you have to learn aside from calculus when you get a college degree. Then there's also other things that these days you need some sort of computing experience, numerical methods, that kind of thing. Then you probably need some experience in whatever field you're going to apply mathematics to. But that's the main thing. Some people go off in other areas, number theory and all sorts of different areas. But for a math degree, usually everybody needs calculus and linear algebra. Those are two subjects. So you'll have to learn this sooner or later. Here it is. A matrix is just a rectangular array of numbers. Just put numbers into rows and columns is all it is. Such as A equals 2, 1, 3, minus 1, 0, 6. Said to be a 2 by 3 matrix, meaning it has 2 rows and 3 columns. That's a matrix. That's all you need to know about it. Here's what a matrix. The braces are just to help you know that it's a matrix. It's notation. But the matrix is actually just this rectangular arrangement of numbers. Now, a square matrix is a matrix that has the same number of rows and columns. So an n by n, same number of rows and columns matrix is called a square matrix. All the stuff building up to the easy definition. Okay. It's like, this word is easy in Russian, but first you have to learn the Russian alphabet, you know? Yeah. All right, so an n by n matrix is a square matrix. And a square matrix has something called a determinant. The determinant of a square 1 by 1 matrix, there's one element in it, is, oops, this looks like an X between ones or something. It's a 1 by 1. Here the X means number of rows and columns. That's another notation that the X can mean. It's not a cross product. All right, 1 by 1 matrix is, what you do is you put the matrix between straight bars instead of square brackets. So you put A, 1, 1. It's only got one row and one column, so there's just one element. Is the number itself. So it's not absolute value. This means determinant of the matrix, and the determinant of the matrix with one element is the one element. That's all it says. So for instance, the determinant of -4 is -4, for example. BG means for example. So it's not an absolute value, it's determinant. And how about a 2 by 2 matrix? A 2 by 2 matrix has determinant, well, it has 4 elements, 2 rows and 2 columns. So we index them like this. A11 will be the number in the first position. A12 is the number in the second position. A21 is the number in this position, and A22 goes here. And they're numbered by rows and columns. The first number is the row number. This is row 1, column 1. This is row 1, column 2, row 2, column 1, row 2, column 2. So these are different indices are in a different order. And this is the matrix. If you put square brackets, you just leave it like that. Oh, it's this array of 4 numbers. But if you make it straight braces, it means the determinant of the matrix, which is a number. And so this means the number, this times this minus this times this. A11, A22, A21, 1, 2. That's the determinant of a 2 by 2 matrix. And all these things in here are just numbers, and so this product is a number. Now, let's leave this one up here. How about a 3 by 3 matrix? What happens is these are defined, or can be defined at least iteratively. And so I like this way of presenting it, because even though we only need 3 by 3 matrices and 2 by 2 matrices here, this shows you exactly how to do 4 by 4s and 5 by 5s and so on that you use in linear algebra and other courses, physics, for instance. Suppose I have A11, A12, A13, 3 numbers in a row, row 1, A21, A23, 2, excuse me, and A23 comprise the second row, and A31, A32, A33 of the third row. So there's square braces, it means the rectangular array of numbers, but the determinant of the matrix means find the number that has this value. It's equal to, so this is a 3 by 3 matrix. Oh, and I should put notation. There's another notation for this too. I guess I'll put it in a moment. Right. Is you take the element in the first row, first column, and you multiply it by the 2 by 2 determinant gotten by wiping out its row and column. This part. A22, A23, A32, A33. And then you subtract the next element in the first row, A12, and you multiply it by the determinant got by wiping out its row and column. So it's these two and these two. A21, A23, 31. Then you add the last element of the first row, A13, times the 2 by 2 determinant got by wiping out its row and column to leave this part. A11, A122, 21, A22, A31, now we already know 2 by 2 determinants from here, so a 3 by 3 determinant you observe is defined in terms of 2 by 2 determinants. So I have A11 times this minus this times this. That's how we did a 2 by 2 determinant. So diagonal minus diagonal. A22, A33, minus A32, 3. And then minus this one, A12, times the determinant A21, A33, minus A31, A23. And then plus A213 here multiplies this times this, A21 times A32, minus A22 times A31. There it is. And if you group all those things out, you find out it's the same as equation 1. So this is an alternate definition. It gives you the same numbers. I'm sorry, it's not doing the cross product of vectors. Sorry. So this is a 3 by 3 determinant. Now we can use the 3 by 3 determinant to write an easy form for memorizing the cross product. Now you have to remember another notation. Also, let me do a 3 by 3 determinant just for fun because we're going to need the 3 by 3 determinant anyway soon. Let's end a 2 by 2 example. What is the determinant of the matrix A with elements 1, minus 1, 3, 2, 1, 4, 5, minus 2, 6. Suppose I took that matrix. What's its determinant? Sometimes written this way. This is another notation. Get A. Or this notation. So this is just two different notations for the same thing. 1, minus 1, 3, 2, 1, 4, 5, minus 2, 6. So this is the matrix of 9 elements. With the straight bars, it means the determinant of that matrix, which is the following number. You take this element, 1, multiply it by this subdeterminant wiping out its row and column, 1, 4, minus 2, 6. Then you subtract the next one, this one here, multiply it by its subdeterminant got by wiping out its row and column, 2, 4, 5, 6. Then you add this last one, 3, times the subdeterminant got by wiping out its row and column, 2, 1, 5. All this work for a number, huh? So let's see, it's 1 times 6. Well, spread out. 1 times 6 minus 2 times 4. Diagonal minus diagonal, taking a 2 by 2 determinant. So the determinant of this matrix is 6 plus 8 is 14, right? And then you add 1 here times 2 times 6 minus 5 times 4 is the determinant of this little 2 by 2 matrix. This times this minus this times this. 12 minus 20 is negative 8. And then finally plus 3 times 2 times minus 2 minus 5 times 1, right? Diagonal minus diagonal. So what we got is 1 times, this determinant came out to be 6 plus 8 is 14. Plus, because we have minus minus, 12 minus 20 is minus 8. Plus 3 times negative 4 minus 5 is negative 9. So we got minus 27, minus 8 is minus 35, plus 14 is negative 21. So the determinant of this matrix is negative. And amazingly, you think, wow, I'm just doing a whole bunch of wild computations. But it turns out to have great geometrical significance, this determinant, in all sorts of ways. Any questions on this one? The determinant of this matrix is this number, negative 21. You can only take determinants if they have the same number of rows as columns. This is a 3-row, 3-column matrix, so we call it a 3 by 3 matrix. And the determinant of the 3 by 3 matrix. This is pronounced 3 by 3. It works like that. Now you can see how to extend this to higher dimensions too. Suppose I had a 4 by 4 determinant. Can you imagine what would happen? I had another row and column out here. What you do is you take this element times the subdeterminant got by the 3 by 3 determinant got by wiping out its row and column, minus this one times its subdeterminant, plus this one times its subdeterminant, minus this one times this subdeterminant. So you use plus, minus, plus, minus. Each element in the first row multiplied by its corresponding 3 by 3 subdeterminant, and going plus, minus, gets you the 4 by 4s. And you can go on with that as long as you want. All right. That's one way to compute determinants. Turns out you can compute determinants in other ways. If you were to, that's called expansion of the first row. You might say, what's so great about the first row? Turns out you can do it in the third row. If you took this one times its subdeterminant, wiping out its row and column, minus this one times its subdeterminant, plus this one times this subdeterminant, you get the same number. And so you can also do it that way. The second row, however, you have to go minus, plus, minus. And so on all the even rows, you take minus this one times subdeterminant, plus this one times subdeterminant, minus this one times subdeterminant, wiping out the row and column. All odd rows, you go plus, minus, plus. That way you can take the determinant on any row, or the same thing on the columns. Right? You can take this one times its subdeterminant, minus this one, plus this one, or you can take minus this one, plus this one, minus this one, each times its subdeterminant. So there's a lot of ways to compute subdeterminants. There's other formulas to compute determinants. And there's other. But we'll just say this is by far the most popular way. Now we'll finally get the easy definition. In terms of these, that is 3 by 3 matrix. A mnemonic. Are you in here? I can't remember. Formula for determinant for a cross product. This B cross W is the determinant gotten by putting the elementary vectors I, J, and K in the first row. And then you put B in the second row, its components in order, and W in the third row. You can compute it as this determinant. Elementary vectors V, W in that order. We'll call this equation 2. This is the easier formula to remember. The other one is the easier formula to execute. People use both. If you forget the first one on the test, just go to this one. Just easy determinant once you know determinants. We have to learn determinant also in this section for another reason. There's something called the scalar triple product that uses it also. So we're going to need it even in this section on other stuff. And then this is with, recall, I in 3 dimensions. In 2 dimensions, the vector 1, 0 along the x-axis. In 3 dimensions, we said it's the vector with components 1, 0, 0, moving 1 unit along the x-axis in 3 dimensions. J, of course, is the second elementary vector, 0, 1, 0. And K is the third elementary vector, 1 unit along the positive z-axis, 0, in that prescription. If you're real insightful on this, you'll realize I've kind of pulled a fast one. This isn't strictly speaking a determinant, right? A determinant, you have to put 9 numbers in, but I put 3 vectors in. But if you compute it the same way, we just call this the determinant, even though the first one technically is. All right, so let's see if we can do that. Oh, I kept the vector all that time. I was gonna distract. That's all right. Let's take the cross product of 1, 2, 4 with 1, 0, minus 2. Suppose I take the cross product of these 2 vectors. What is that? We have a formula 1. Let's try it by formula 2 to the determinant. All you have to do is put I, J, K in the first row. With this vector in the second, 1, 2, 4. This vector in the third, 1, 0, minus 2. All you have to do is remember how to do a determinant, and you can get the cross product of those 2 numbers. I think that's what engineers remember more than the first definition, because this is just easier if you don't use it every day. Easy to remember. So what do we get? Remember how to compute the 3 by 3 determinant. You take this element, now it's a vector, but we'll still do it the same, times this subdeterminant got by wiping out its row and column. Right? Let's scratch this out and this out. We get 2, 4, 0, minus 2. Then we subtract J times its subdeterminant, wiping out its row and column. 1, 4, 1, minus 2. Then we add K times its subdeterminant, wipe out its row and column. 1, 2, 1, 0. There it is. Now I have to be able to do these 2 by 2 determinants. Those are easy, right? Just this times this minus this times this. So that's I times, I'll write it out in detail here, and I'll start taking the speed up soon. 2 times minus 2 minus 0 times 4. This 2 by 2 is something, right? Minus J times 1 times negative 2 minus 1 times 4. This times this minus this times. Plus K times 1 times 0 minus 1 times 2. So what have I got? Let's see. Negative 4 minus 0 is negative 4, all multiplying I. Then negative 2 minus 4 is negative 6. Multiplying negative j is plus 6j. Sometimes these canceling minuses get to be tricky. And then 0 minus 2, k, I get minus 2k. There's the cross product. Or if you prefer the first notation, the component notation, you can also write it this way. It means the same thing, right? Minus 4, 6, minus 2. These are 2 notations for exactly the same thing we showed before. Let's say or. So either one is the same thing. Cross product of these 2 vectors is this vector. You might observe that, boy, there's a chance of mistake in there. There's an awful lot of multiplying. Isn't there some easy way to check this? It turns out there is. So it's real nice that that exists. Just like the dot product may have surprised you, they had so many applications like finding the angle between vectors and determining when 2 vectors were perpendicular or formed an acute angle and an obtuse angle, or how to compute a projection. All that stuff came out of the dot product. just so there's a lot of neat stuff that comes out of the cross product. It occurs in Maxwell's equations for electromagnetism, for instance. It's fundamental. All your electric devices work on Maxwell's equations, and everything from your computer to your cell phone, everything else, and they all have cross products in their laws there. Among other things, there's lots of other applications we'll see here in the text. All right, so now we have some theorems. This is why the cross product is so important. This is one of the theorems. For any two vectors v and w, always the length of the cross product, v with w, is length of v, length of w, times sine of theta, where theta equals the angle between them. Now, if one of them is a zero vector, then what's the angle between them? Well, it's undefined, but it doesn't matter because the length of the zero vector is zero, and so this whole thing will be zero. So, when v and w are not equal to the zero vector, the vector of all components zero, then you do this, and otherwise the cross product is zero. All right. Well, that looks so much like the formula we had for dot product, right? The dot product of v with w was length of v, length of w, cosine of the angle between. Although you didn't need length on this side because the dot product was already a number. And so it's the length times cosine of the angle between them has some significance. Maybe this one does too. Of course it does. So one application the cross product is zero. When was the dot product zero? Remember that? The dot product was zero if they were orthogonal, which meant they were either perpendicular or at least one of them was the zero vector, zero vector being orthogonal. So the cross product, the dot product is a good way of checking if vectors were perpendicular. They were perpendicular if the dot product was zero. Similarly, the cross product, evidently zero. If and only if, IF means if and only if, v and w are parallel, including that the zero vectors are parallel to every vector. Dot product zero when they're perpendicular, the cross product zero when they're parallel. And you can see exactly why, right? V from this theorem up here, the length of V cross W, well, let's say V cross W is the zero vector if and only if the length of V cross W is zero, right? Only if the zero vector has zero length. This one doesn't have a vector on top because it's the length. This one's the vector, which is true if and only if, by the theorem, length of V, length of W, sine of the angle is equal to zero, which is true if and only if V is the zero vector, so its length is zero here, right? It's a product of three numbers. Either this number is zero, or this one is zero, or this one's zero by the zero product property. That's the only way you get a product of zero. I mean, it's either V is the zero vector, W is the zero vector, theta equals 0 or theta equals pi radians. These are two parallel cases. One is the same direction, one is the opposite direction, but that's the only way you can make sine of an angle between 0 and 180 degrees equal to 0. And so that's the reason. So this is true if and only if they're parallel. Assuming you count the 0 vectors parallel to everything. All right, so parallel is equivalent to this, is equivalent to this, equivalent to that, is equivalent to that. And you can tell they're parallel anyway. It's not like this gives you some great new insight. How do you tell if vectors are parallel in the first place? Remember, vectors are parallel if one's a multiple of the other. So you just look at them and see if they're a multiple of each other. But nonetheless, if you get some theoretical computation and it predicts that the cross product is 0, then you know they're parallel vectors. They're just multiples, one to multiple. Right. So you can tell this by inspection if they actually give you the vectors. But nonetheless, that's a useful geometrical fact. Second interesting geometrical fact is if you have a parallelogram, the area of the parallelogram determined by vectors v and w at a given point P is basically the length of the cross product. So it computes the area of a parallelogram, which actually is more fundamental than you'd realize. In calculus 4, you don't actually spend much time on this, but it's sitting there behind the scenes. If you go to a different coordinate system where the axes aren't orthogonal, but like this, instead of adding up little rectangles to get areas, you add up little parallelograms. And so this cross product is fundamental for adding up the little parallelogram areas, of the theory behind adding all those up. So it comes in interesting applications like that. But here it is, the area of a parallelogram. And here's the reason for the proof. If you take any parallelogram determined by V and W, what do I mean the parallelogram determined by V and W to point P? I mean, there's only one parallelogram with these two as two of the sides, right? I take this V and slide it over here to make a parallel side, or a copy of V. I take W and parallel transport it up here to make a copy of W. And that's the parallelogram they determine. I just take one copy of this over here and a copy of this up here. There's only one parallelogram, right? Now, what's its area? Well, it's quite easy with this little trick. I partly just like showing you this because it's a nice geometrical trick that you see again somewhere. Drop a perpendicular here. This little triangle you can then take and insert it up here, and it fits just right, to make a rectangle. So the area of the parallelogram, A, is equal to the area of the rectangle that I formed by moving that little triangle. Right? Well, what is the area of the rectangle? Oh, it's base times height, right? What's the base? Well, it's this part, but that's the same as this part, this rectangle, which is the length of W. So the base is the length of W, because it's this, or this, or this. And then what's the height? The height here, H, what is that? Think about it. On any right triangle, this just comes out of trigonometry. The opposite side length is equal to the hypotenuse times the sine of the angle in here, theta. So it's hypotenuse length of V, the sine of the angle. That way, this over V, length of V, gives you sine theta, right? So this is length of V sine theta, so that this over this is sine theta, opposite over adjacent, opposite over hypotenuse is sine theta. So if the height is length of V sine theta, well, look at that, length of V, length of W, sine of the angle between them. And I forgot to put one thing here. Let's see. No, that's right. This is just the length of V cross W by our previous thing. So there it is. I'll put QED, which means which quod erat demonstratum in Latin, means which was to be shown. You see that in old textbook? It's kind of fun to put that in. It makes it sound like you good at proofs or something. Quod erat demonstratum. Now, forgive my terrible pronunciation of Latin, but it doesn't matter. All the Romans are dead. Nobody says how to pronounce it. Except maybe a Catholic priest. Which was to be shown, it means. All right, now let's do that to do this even more interesting problem. Example, find the area of this triangle laying cockeye in three-dimensional space. Suppose the triangle has vertices. One, 3, minus 1, 2, 4, 1, and minus 2, minus 3, 5. Those are 3 vertices, right? What's the area of the triangle? This is kind of a hard problem. I just lying at some cockeyed angle in three-dimensional space. How do you figure its area? Well, what you can do is you can take the vector v. If I call this P, call this point Q, call this point R. Let's take the vector V from P to Q, right? What we do is we subtract coordinates, 2 minus 1, 2 minus 3, 1 minus negative 1. That's the vector from P to Q, right? As those components. 1, 1, 2. Now I'm going to take the vector W and make it the vector from P to R, let's say. So I subtract the components, this one minus this one, minus 2 minus 1, minus 3 minus 3, 5 minus a negative 1. This vector has components, negative 3, negative 6, 6. There's vector W. How am I going to find area of the triangle that has those edges? So if you really think about it, here's P. This is not drawn oriented correctly or with the right angle between them. I'm just saying there's a vector from P to Q, and there's a vector from P to R, and this holds in general, not to produce this one. The triangle area here is exactly 1/2 of the parallelogram area. I'm putting a copy of PQ up here and a copy of PR over here. So the area of the triangle is 1/2 parallelogram area by symmetry. Take this one, flip it over the other way, and it's the same triangle. Which is 1/2 B cross W. All I have to do is compute the cross product, divide by 2. I find an area of any triangle. So it's quite easy. You know, we haven't even gotten to the calculus of this stuff yet. There's nice calculus formulas for these too. It turns out that the dot product and cross product both follow a product rule for taking derivatives. So it's kind of nice for calculus, it turns out too. So there's the triangle. I just have to compute that cross product? Well, I can do it either one of the two ways. Want to do it the fast way or the determinant way? Preference way? Okay, let's go with the fast way then. So this is equal to 1/2 length of, and I'll take 2, 3 minus 3, 2. So it's 1 times 6 minus 6 times 2. Or 2 times minus 6, I should put it. Doesn't matter. Right? 2, 3 minus 2. Then I'll take 3, 1 minus 1, 3. 2 times minus 3 minus 1 times 6. And then 1, 2 minus 2, 1. 1 times 6 minus 1 times minus 3. Well, let's see, it's 1/2 the length of the vector. 6 plus 12 is 18. Minus 6 is minus 12. 6 plus 3 is 9. So the cross product of those two vectors (18 minus 12) well, how are we going to figure out the length of that thing? Those are big numbers. You can do it in your calculator, of course, but I'll make this recommendation. If you rewrite this as 1/2 the length of 3 times the vector, 6 minus 4, 3. Remember, the length of a number times a vector is the absolute value of the number. This means absolute value, not determinant. Times the length of the remaining vector. So I can just find the length of this vector instead and multiply by 3. That'd be easier, right? So what's the length of this one? You just root some square them, right? We said that's 6 squared plus minus 4 squared plus 3 squared by the Pythagorean length in 3 dimensions. 36 plus 16 is 52, plus 9 is 61. So this is square root of 61. It's this one. Evidently, I have that times 3 halves. So it's 3 square root 61. That triangle. Let me tough finding it without the cross product, doing it.
Ask a question like this on our test, what we get to pick between the determinant form to do it or this or.
Yeah, I'll let you do whichever way you want on the test. I won't tell you to do it one way or another. Either use the fast one or the determinant. Okay. We can step it up one more, huh? That's all right. The scalar triple product of 3 vectors, D, U, V, W. Now, if you can take the dot and cross product of 2, you can take the dot and the cross product, and you can get this. There's different notation. Some books put this vertically, or some put commas between it, I think. I'll just put U, V, W like this. And if you put that notation, it means find to be U dot V cross W. Now the question is, which comes first, the chicken or the egg, right? Does the dot product come first or the cross product come first? The answer is the cross product has to come first, because if you do the dot product, you get a number, and the cross product is not defined with a number, right? So there's only one order you can do it. It's this order. So you don't need the parentheses, but when you write it, it means this. Now, if you really think about this, there's an easy way to compute this triple scalar product. Let's find it. Easy, if you really think about it. Triple scalar product, U dot V cross W. Means you're taking the dot product of U with the vector that's this determinant, I, J, K, V1, V2, V3, W1, W2, W3, right? Using the cross product formula. What's that, obviously? Well, let's put it more obviously. U is the vector, U1, U2, dot product with this. How do you dot product two vectors? Multiply their first components and second components and third components and add them all together, right? That's exactly what you get if you replace I with U1, J with U2, and K with U3. It makes U1 multiply what used to multiply I, which is the first component of this vector. Makes U2 multiply the second component of this, whatever multiplies J, and U3 multiply whatever multiply K, and add them all together. So this is, in fact, this determinant. The triple scalar product, which has nice uses in physical sciences, is nothing more than the determinant matrix with U, W, all in rows. How about that? What's more, it has geometrical significance. This is the calculational formula. We call that 3A or something. This is the definition of triple scalar product, U dot V cross W. This is the calculational formula to do it faster. Just do the determinant. Here's the theorem that says this has useful applications. There's more than this actually, but volume in free space of the parallel pipet. Parallel pipet is anybody? It's a six-sided figure with polygon with sides that are interiors are polygons that are parallelogram. So it's got six parallelogram sides of three-dimensional space like this. You take these three line segments and then you complete a parallelogram with these here. Then you complete a parallelogram with, well, show it more room. Complete a parallelogram with these, complete a parallelogram with these, then you complete a parallelogram with these, and then you do it on the other sides. A special case of this is a six-sided die, right? If you make all the angles right angles, you get a rectangular box, and if all the edges are the same length too, then it's a square box, right? But this is a rectangular parallel, this is a parallel pipe. And suppose that you determine the parallel pipet by picking three vectors emanating from the same point, much like what we did for the parallelogram in the plane. Now we'll do a parallel pipet in free space. Here's U. How I want to try a little differently. Better. Here's V. Here's W. They form a parallelogram base. Then let's have this be U up here. This is how I'm used to drawing it. Then you make a parallel pipet, like filling this out, right? So a rectangular box is also called a rectangular parallel pipe because it's parallel pipet with all right angles. Right. Now, what's the volume of that box? Well, we already know the area of the base is what? Parallelogram, so its area length of B cross W, right? Our previous. What's the volume of the box? Well, when you slide this rectangular parallelogram base like that, the volume that's constructed just by definition of volume is the area of the base times the height that you slide it. So if you slide it a height h, then its volume is the area of the base, the height, right? What's the height? Well, if you run it over here, it is all this angle. Yeah, all this angle theta. And then what is the length of this side? This is length of u, hypotenuse, times the cosine of theta, right? This is the adjacent side of theta. The length of u cosine theta, this by trigonometry is the length of the side, so that this over this is cosine of theta. That's h. So the area of the base is this, the height is this. And if you take area of the base times the height to get the volume, you get length of B cross W times length of U times cosine theta, where theta is actually the angle between U cross B and W. This is actually the direction. I need to write this down before. I'm sorry I didn't. But this is the direction of B cross W is up here somewhere. And so this is actually the dot product, right? Length of a vector, length of another vector, cosine of the angle between them is the dot product of U with B cross W. QED, right? So in this, I use that actually this is the vector B cross W, which we'll talk about. All right, so now, so the volume of the parallelogram determined by determined by the three vectors u, v, and w at a point P is, so this will prove the following statement. If a volume equals the absolute value of the scalar triple product. Why do I need absolute value? I left out a subtlety in the proof here. I said this is h. Actually, if the angle is down here, clearly is obtuse, then cosine is negative. So h is actually length of u times the absolute value of the cosine. In case it went down the other way and made an obtuse angle, which now makes it this absolute value of all this stuff. Since these are already positive, the absolute value is that of the cosine. So there's the volume formula. The absolute value of the scalar triple product is the volume of the parallelogram. Parallel hypotenuse. We can try that one. Example, find the volume of the parallelepiped determined by the three vectors, 1, 2, 1, minus 4, 4, minus 1, 0, 2, 0, 1. Say vectors all at the origin. O for origin. Doesn't matter where they are, it's the same volume, but we'll put them at the origin. What's the volume? It's as easy as taking the absolute value of the determinant. And now we run into a notational inconvenience. The volume is the absolute value of the triple scalar product. But the triple scalar product is evaluated most quickly as a determinant. So if I put determinant here, then I've got straight bars for the determinant and straight bars for the absolute value, a collision of notation. So maybe I'll change my notation here. And instead of writing straight bars for absolute value, I'll say ABS for absolute value. That's what's using computer programming is ABS. So this is the absolute value of the determinant then, gotten by putting these all into a matrix, just in order, right? 1, 2, 1, 4, minus 1, 0, 2, 0, 1. All I have to do is take the absolute value of that determinant. Nothing more than that. Defining the volume of a parallelepiped. And these are actually important in doing calculus in 3 dimensions next semester. Going to parallelepiped. It's not that you do calculations with them, but they're kind of behind the scenes. The reason your calculations work. So what is this? This is the absolute value of, we'll do it the fast way, right? It's one time for a 3 by 3 determinant. This one times this subdeterminant. Minus 1 times 1, minus 0 times 0. Right? Minus 2 times, like I just wrote in column, 4 times 1 minus 2 times 0. It's 4 minus 0. So I'm doing it quickly here. Plus the last element. So I'm expanding in the first row. This one times this subdeterminant minus this one times this subdeterminant plus this one times this subdeterminant. This one. 4 times 0 is 0. Minus 2 times minus 1 is minus a negative 2. Right. So it's the absolute value of all of this. Well, let's see, there's negative 1. Negative 8 more makes negative 9. Plus 2 is negative 7. This parallelepiped has volume 7 as quickly as that. All it is absolute value of a determinant. What's more, there's this beautiful result. This is an easy one to prove also. Theorem. You take V dot E cross W. Or if you take W dot E cross W. What do we get? Oh, wait a minute, it's a triple scalar product, right? So it's V1, V2, V3, V1, V2, V3 again, W1, W2, W3. And something you might have learned if you ever took linear algebra and did determinants before, if one row is a multiple of another, doesn't matter what multiple it is, the determinant is always 0. So here we actually have a repeated row. Because we have a repeated row, if you calculate this, this will be 0. So if one row is a multiple of another, or one column a multiple of another, I'll just appeal to this linear algebra result. And we can multiply this out and see it. But I think more generally, it's nice to know when you see one row multiple with another. You prove that linear algebra. This one is W1, W2, W3, V1, V2, V3, W1, W2, W. Oh, wait a minute, another repeated row. The first row and the third row are multiples of each other. So this determinant is equal to 0 also. What does that tell us? This is a major geometrical application. So these things are both 0, therefore, V cross W is orthogonal. Right, that's what orthogonal means. The definition of orthogonal is they're called orthogonal if the dot product is 0. The reason being that means either the vectors have to meet at right angles or one of them, at least one of them is a 0 vector. So we define it that way, but because it forces them at right angles. So V dot cross W is therefore orthogonal to both V and W. Moreover, we won't prove this here, because we're almost out of time. It turns out by the right-hand rule, because there's always this thing, if you take two vectors, V and W, by orthogonal, do you mean this direction, perpendicular to both V and W, or do you mean this direction? What is it? It's a perpendicular vector up and a perpendicular vector down. What you do is you take your right hand, point your fingers direction of V and turn them towards W, and the direction your thumb points is the cross product. So this is V cross W. And this one is not V cross W. What is it? I think it's the same length, the opposite direction it is minus V cross W. Which brings out an interesting thing into play. What if I took W cross V? I start in the direction of W, turn this way. By the right-hand rule, this would be W cross V. And this would be minus W cross V. And what that shows is actually the cross product is not commutative. You have all these nice properties of the dot product, like it distributes over addition, right? It's commutative. You can take the dot product in either order. Not so with the cross product. All the properties hold that you'd like to see, right? It does distribute over addition. V cross U plus W is equal to V cross U plus V cross W. Right? So it distributes. If you take C times V cross W, it's the same as C times V cross W is the same as V cross CW. And so you can do all these kind of properties that you'd like to see. If you take V, you have an associative property, V cross W cross U actually has this associative property. It's V, we won't prove all these, it's too long. V cross W cross U, you can do that. All these properties hold, but what did we just show over here? One property doesn't. V cross W is not equal to W cross V, it's equal to minus W cross V. It's anti-commutative. But it is associative, right? As a distributive law. It's all those kinds of nice things, but it's anti-commutative by this last rule. Now, this is of immense importance when we go to do geometry with planes, because when we want to construct a plane using two vectors in the plane, we need a vector perpendicular to the plane to determine its equation, and that's precisely what we get out of the cross product. So this will be a lot of geometrical help. But if you take V cross W or W cross V is perpendicular to both W and V, so V dot V cross W or W dot V cross W is always equal to 0. This brings up interesting corollaries, if you're right. Corollaries of theorem that follows quickly from another theorem. What do you think I cross J is? You're to draw them in a plane. Here's I is 1 unit along the x-axis out to the point 1, 0, 0. Here's J along the y-axis out to the point 0, 1, 0. And here's K, the unit vector along the z-axis to the point 0, 0, 1. What do you think I cross J is? Well, we know what its length is, right? Its length, I cross J, length of I, length of J, sine of the angle between them, right? Our big theorem there for geometry. But length of the unit vector is 1, right? This vector root sum squared its components, its length is 1. I, J, and K are unit vectors. J has length 1. And what's sine of theta? The angle between the I and J vectors, they're axes, so it's 90 degrees. This is 1. So I cross J has length 1. What directions does it point? It points in the direction of the z-axis because it's perpendicular to the x and y axis, right? There's only one answer it can be, and you can compute it by doing the cross product. You'll see if you do it directly. You get K. You can also just compute the cross product directly to see. I cross J is K. Similarly, you can do the other ones. I cross J is K. J cross K is I. And K cross I. J, be careful to do them in cyclic order. If you cross J cross I gives you minus K, for instance. Also, we have this wonderful property, the triple scalar product as a result of this. If you take U, V, W, turns out you can cyclically permute these. You can rotate these around and say this is W, U, V, the triple scalar product. Is V, W, U. You can rotate them around. Rotate W to the front, rotate V to the front, rotate V. Those are all equal, but they're all equal to minus if you interchange the order of two. U, W, V, interchange any order, because this is the cross product. This means U cross dot V cross W. When you interchange those two, it's a cross product, you get a minus sign. So you get this one, and you have to take the cross product in reverse order, you get minus sign. So it's minus this one, and then you can permute these cyclically. V, U, W, and W, V, U. So the triple scalar product of any three vectors is always equal to within a minus sign. 3 of them are equal, and 3 of them are equal to minus that. Gives you some interesting relations. Well, let me put some homework up to look at on these. We might have a couple follow-up comments left. Got quite a many examples, right? But here's the ones to look at. 11.4, 3, 11, 13, 19, 21. These are mostly pretty easy. 25 and 27. By the way, I should say also a lot of math books, that's the physics way of doing this cross product. A lot of math books like to use the first 3 fingers and say, put thumb in the direction of V, the index finger in the direction of W, and then your middle finger points in the direction of cross W. So if you use your right hand, if you use your left hand, then it points the wrong direction. And this is almost ubiquitous that you do them in this order, because the same order as the axis keeps right-handed systems. So you got I cross J, you get K. But I have seen, I think I mentioned before, in Russian aircraft, sometimes they like to point, a vertical direction so that they use left-handed coordinate systems. If you think the order isn't important, if you study biology, you find all life is based on left-handed amino acids. And so actually, life itself depends on being left-handed. and the right-handed doesn't work. So it is actually an important property of life itself. That's it for today. We'll pick it up next time. Thank you, online.